This presentation will focus on how the Great Lakes influence the weather across the region, with a special emphasis on aviation weather. In this presentation, we will talk about lake effect precipitation, fog, the lake breeze, and the effects the Great Lakes have on thunderstorms. One of the main things needed to produce lake effect snow is for the air mass advecting across the lake to be much colder than the water temperature. We're generally looking for the air mass to be a good 10 degrees Fahrenheit or colder. The colder the air mass, the greater the heat and moisture flux off the lake. As the air mass is modified by the relatively warm water, the heat flux lifts the inversion base and the moisture condenses into snow on the downwind side of the lake. Winds converge along the shoreline as the friction over the land slows the wind speeds. This added convergence aids the lifting of air parcels upwards and contributes to the intensity of snow on the downwind side of the lake. Also note that the initial stages of cloud development over the lake occur in bands. Shoreline orientation on the upwind side of the lake can enhance some of these bands. This diagram provides additional illustrations to the lake effect process. Note in the bottom image that the fetch is important. In other words, the longer the air parcel resides over the open water, the more heat and moisture flux occurs. So a northerly wind over Lake Michigan, for instance, will lead to a better response than, say, a west to east wind oriented over Lake Michigan. Locations with terrain on the downwind side of the lake have another added source of lift, and that is orographic. Locations in the Great Lakes region where the terrain rises sharply downwind of the lakes are the western and central UP, northwest lower Michigan, and upstate New York. The direction of the mean low-level winds will determine what locations downwind of the lakes are impacted. This image shows a northwest to west wind flow, which is the most common during the wintertime. Note how the west side of lower Michigan and the northern side of the UP get impacted under this wind regime. In this image, we have typical northwest flow lake effect snow shown by a composite of regional radar data. An important point here to make is that because the lake effect snow is relatively shallow, with tops on the order of 6,000 to 10,000 feet, the farther away you get from the radar, the higher the radar beam and more likely that the base of the radar beam will overshoot the top of the snowfall. In this image, the radar is overshooting the snow near Ludington, as well as off the northwest tip of the thumb, because in lower Michigan, the three radar sites are at Grand Rapids, White Lake, which is outside of Detroit, and Gaylord in north central lower Michigan. So even though the image looks like no snow is falling in, say, Ludington or the tip of the thumb, these locations are actually indeed getting snow. On a final note, while this actual radar image is quite dated, the fact that the radar beam overshoots the snow that far out still holds true today. In this event was a rare early season Arctic air outbreak. It occurred in mid-October of 2006, and we had heavy lake effect snow over Buffalo, New York, which amounted to 1 to 3 feet. In this case, Arctic air under southwest winds will target Buffalo. With the southwest wind, the air parcels have a long residence time over Lake Erie due to the shape of the lake. During situations with Arctic air under a north-northwest wind, we often see far southwest lower Michigan, specifically Berrien County, get targeted with the heavier lake effect. Most often there is incredible variability within lake effect. Between the bands of lake effect snow, skies are often clear. Within the bands of heavy snow, visibility can quickly drop to near zero. In the image on the top there, we are in between snow bands, and you can see the clear blue skies. In the bottom image is an aerial view of downtown Buffalo, New York, and you can see one side of the city being covered by heavy lake effect snow off of Lake Erie. Lake effect season runs during the time of year when the Great Lakes are warmer than the surrounding air masses. This would be early fall through mid to late winter. Yes, lake effect does diminish when the lakes freeze over. If, however, there is open water, a very cold air mass in late winter can still generate lake effect precipitation. Even when the air mass is just a little colder than the water, the moisture flux can be enough to generate clouds. These clouds usually get trapped under a strong low-level inversion and spread out and downwind from the lake. Oftentimes the inversion is too strong to where the cold air isn't deep enough to cause lake effect snow. It does, however, result in a nice thick blanket of stratus clouds. In this example here, we see an atmospheric sounding representing a deep low-level inversion with moisture trapped underneath. Right here is the inversion. That is where the temperature increases with height. And right about in here is where the saturation is, where the temperature and the dew point come together. So you have this low-level saturation below a deep inversion, which is what is trapping the stratus underneath, often common in the wintertime in the Great Lakes. Wind convergence along the shoreline can give an added source of lift which can aid in cloud development. The increased friction along the shoreline will not only slow the wind speed down, but will alter its direction a bit, which oftentimes enhances the low-level convergence on the downwind side of the lake. And in the top left, we see image of stratus on a beach, pretty typical in the wintertime. And the image below is a satellite view of lake effect snow, but with the clouds spreading out in a continuous strata-Q field across southern Michigan. Lake effect clouds and precipitation are also regions of enhanced icing concern, as the heat and moisture flux off the lake produce supercooled liquid cloud droplets into a sub-freezing air. Again, the risk is going to be on the downwind side of the lakes. The icing risk is enhanced when temperatures are near freezing and there is wet snow. This is an example from an Aviation Weather Center forecast of an icing event as a result of lake effect snow. You can see that in this case here we have a westerly flow over Lake Michigan, and you can see how it enhances the icing risk across far southern lower Michigan. And the next section will discuss two types of fog: springtime advection fog and radiation/advection fog events during the fall. Advection fog events are common when we get the first intrusions of humid air into the region, typically during the springtime. The lakes at this time of year are very cold, so once this moist air overspreads the cold water, the air is cooled and the high moisture content quickly condenses into cloud droplets near the ground, or fog. Because of the reliance to the cold water, these events typically only impact locations near the shores of the Great Lakes, generally within a couple miles. However, if the prevailing winds are a little stronger, they can advance up to 50 miles inland. The spring is the typical time of year again when we see these warm humid air masses infiltrate the cold Great Lakes. Often the fog becomes very dense and can reach several hundred feet thick. Usually the fog develops over the lakes during the night or early morning hours. Then winds push the fog inland during the morning, and daytime heating will eventually erode the fog over the land. In this diagram, we see winds bringing the fog inland. The increased heating and mixing over the land typically causes the fog to rapidly decrease as it moves inland during the course of the day. This is a picture of a fog bank taken from a fisherman over Lake Michigan in early May of 2014. In the top left here, we see a satellite view of fog over east central Lake Huron. The bottom left, in this case, we have easterly winds pushing the fog across the western portions of Lake Superior. Duluth, Minnesota often gets socked in fog in these scenarios. And on the right, we have a moist southerly winds causing extensive fog over Lake Michigan. There are several communities along the shoreline that are in dense fog, but just a little ways inland, we have no fog at all. The top image here is of the Grand Hotel on Mackinac Island. The Straits of Mackinac see this type of fog in the spring often. It is usually caused by either a moist southeast wind off Lake Huron or a moist southwest wind off of Lake Michigan. The bottom two images are from Chicago. A moist easterly wind can bring fog off Lake Michigan inland. Oftentimes, again, we'll see the fog move inland during the morning with the mean winds. The onset of daytime heating will then erode the fog quickly over the land. Before the fog dissipates, it usually lifts to an IFR or LIFR ceiling. This type of fog, however, can persist much longer near the shore and especially on islands. Islands that are particularly susceptible are Mackinac Island and Beaver Island. During the beginning of summer, these events become less common as the lakes, especially the water close to shore, begin to warm. You can, however, still get fog over the colder middle portions of the lake, but it is less likely to push towards the shore. In forecasting these events, we typically look for the dew points of the moist air mass to be a good 10 degrees or more higher than the lake temperature. One of the big problems in forecasting, however, is that the water temperatures vary considerably across the lakes. There is also often uncertainty as to the depth of the marine layer, which affects how quickly the fog dissipates over land. The top of the marine layer is marked by the base of a shallow inversion. The larger scale pressure patterns influence the depth of these inversions. During strong high pressure, the marine layer will be shallow and have a much more difficult time sustaining fog too far inland. During weaker high pressure or low pressure systems, the greater depth of the marine layer makes it more likely to push inland. During deeper low pressure situations, the fog often lifts to a stratus deck, which can be fairly persistent inland from the lakes. Now we're going to turn our attention to radiation advection fog hybrid events in the fall. Radiation fog occurs when clear skies and light winds at night, which is often associated with high pressure, cool the air to saturation, causing fog formation. This is more efficient during the fall and winter when the nights are longer. Also during the fall, the Great Lakes are still very warm. So an onshore wind during the day can bring this warmer and more moist air mass inland. The air will then reach saturation more quickly during the nighttime cooling due to the added moisture from the warm lakes. So again, an onshore wind will bring this warmer and more moisture-laden air mass from the water inland. and during ideal radiational cooling conditions at night, the moist air mass that advanced inland from the lakes cools and reaches saturation, allowing fog to develop. The image in the top left is actually of the Gulf coastal region, but is used to illustrate the point made in the previous slide. The other image is an IR satellite image showing dense fog over Metro Detroit and portions of northwest Ohio. This image was taken in the morning in November. Light easterly winds over Lake Erie overnight and during the previous day allowed the moist air residing over the lake to advance inland. Clear skies and light winds over the land during the nighttime caused the cooling to condense the moisture into a dense fog. Visibilities within the fog were near zero at times. These events tend to be hard to predict. It is usually very difficult to determine how far inland the fog will develop. When the shoreline downwind of the lake is relatively flat, the moisture will push more easily inland. So again, these type of events form near the shoreline during the night, and they tend to slowly push inland during the morning in the direction of the winds atop the fog layer. The winds, of course, should not be too strong as to mix the fog out. In many cases, this type of fog can be very dense, and given the low sun angle in the fall, particularly late fall, this type of fog may take into the afternoon before it completely diminishes. The next section will discuss the lake breeze front. The greater the temperature difference between the land and the Great Lakes, the stronger the lake breeze will be. So spring and early summer usually have the strongest lake breezes, but they do occur any time of the year as long as the land becomes warmer than the water. What happens is that the daytime heating warms the air over the land and makes it become less dense, meaning the pressure is lower than the air over the cooler water. Since air will naturally move from areas of higher pressure to areas of lower pressure, the air will move from the cooler, more dense lake surface inland to the warmer, less dense air mass over the land, which creates an onshore breeze. This is a diagram to illustrate the lake breeze. Note that it is actually a circulation that has a return offshore component higher up, say 5 to 8 kilometers in this case. Usually it's between 1,500 and 3,000 feet. This diagram shows the development of the lake breeze during the day. Also take note that at night, the circulation actually reverses itself and flow near the shore becomes offshore as the land cools more dramatically than over the water. So essentially at night, the whole process reverses itself. This diagram gives another illustration of that point by showing the lake breeze, or near the oceans, a sea breeze. Shows this lake breeze circulation during the daytime at top and nighttime at the bottom. These are how the lake breezes would look on radar. The fine line is caused by returns from dust and insects that get caught along the lead edge of the lake breeze, or the so-called lake breeze front. This front marks where the wind shift and temperature drop occurs. This is a satellite view of Lake Erie during the day in the summer. The clear portions along the edge of the lake mark where the stable marine layer has moved inland. The lead edge of where the clouds start is the lake breeze front. It is important to note that strong offshore gradient winds will inhibit the formation of the lake breeze circulation. If there is an offshore wind greater than 15 knots, the lake breeze may actually not be able to develop. The weaker the offshore flow, the farther inland the lake breeze will advance. The lake breeze is typically marked by an abrupt wind shift and rapid drop in temperature. In most instances, the lake breeze advances 10 to 15 miles inland. Oftentimes during the evening, with the loss of strong heating from the sun, the lake breeze makes a last-minute push several miles inland before diminishing. The final section will briefly touch on the complexities of how the Great Lakes influence thunderstorms. Lake breeze fronts act like a small cold front and provide a source of lift for air parcels and thereby can trigger thunderstorm development. The image on the left is over the Niagara Peninsula in Ontario. The collision of the two lake breezes from Lake Huron and Erie caused enough lift to develop a thunderstorm. The image on the right are storms that developed over western Michigan along the lake breeze convergence from Lake Michigan. Cooler and much more stable air will advance in behind the lake breeze and actually hinder thunderstorm development. You can see in the image here how this stable air around Lake Ontario has even suppressed afternoon cumulus development. From this slide, it should be obvious that forecasting thunderstorms in the Great Lakes region is actually very complex. There are a lot of influences created by the lakes that can both weaken storms and actually enhance them. First off, looking at cases in which the Great Lakes enhance thunderstorm development. One, convergence along the lake breeze front over western Michigan may enhance storms moving into eastern Michigan. Next, the warmer lake temperatures in the fall can enhance thunderstorms by giving them an added boost of moisture and heat. And the shoreline convergence on the downwind side of the lake can cause storms crossing Lake Michigan to rapidly intensify once they reach the western Michigan shoreline. Now there are cases where the Great Lakes suppress thunderstorm development. Strong storms over Wisconsin often weaken once they reach the cold, stable waters of Lake Michigan. In some instances, strong westerly winds bring the Lake Michigan stable layer well inland, greatly reducing the chances for storms over eastern lower Michigan. Now, one case that I want to point out, large thunderstorm complexes and squall lines typically occur with very high instability aloft, often very unstable above the shallow marine layer. The result is that the storms are actually not impacted much by the Great Lakes, as they tend to just ride right over top of the shallow stable layer over the lake. This is a still radar image from July 11, 2011. Strong storms developed in the lee of Lake Michigan around Kalamazoo and Grand Rapids and moved east. Meanwhile, Lake Michigan is having no effect in weakening the squall line, which is moving in from the Chicago-Milwaukee regions. That squall line, in fact, produced a swath of strong damaging winds across southern Michigan. And that's the end to this presentation.